So imaging and vision systems, especially in an automotive context, have to deal with extreme imaging scenarios, going from very, very high light levels due to sunlight illumination, highly reflective objects, all the way down to extreme low light objects in the peripheries. And all of these very challenging hard imaging conditions have severe impacts, especially in the automotive world. So other than cell phone imaging here, we really deal about systems that are safety critical. And here's an example. Here's a very extreme example just to show you the effect on state-of-the-art vision, higher level image analysis. On the left side, you see an image, which is an ultra-low light image acquired of a scene out in Montreal. And so this is an image which is a contrast normalized image, so very, very low signal here. You can see that very, very severe noise. You see streak artifacts from the sensor, and you can see here that a state-of-the-art detector, such as faster RCNN, some modification to achieve state-of-the-art performance on COCO and other JPEG data sets, actually completely fails in this scenario. On the right side, you see a bunch of more challenging cases where you have reflections on the road here, artificially severe aberrations, but you can get similar cases in realistic automotive systems all the time. So you can see here that here's a pretty fast one. Google's SSD also fails in these scenarios here. So let's look at a common automotive test scene that is used for assessing the image quality of an automotive imaging system and vision system. So what we have here in this test scene, what's simulated here, are optical aberrations, such as the one that I showed you, an extreme case on the previous slide. So you see the effect of headlights on the optics, introducing severe glare in this case, and spread of a point spread function because of the high illumination. What you can also see here are, and this especially matters for rear view cameras, optical geometric distortion, severe chromatic aberrations due to severe off-axis PSF spread. What you can also evaluate with such a test scene to a certain extent is the naturalness of the scene. Sharpness, of course, the traditional checkerboard pattern features can be seen in the scene here. Fairly extreme range of contrast levels can be measured. Color fidelity, structure in shadows, extremely important to perform vision in such areas. And noise handling, of course, in such low light scenes where it really matters and traditional ISPs fail. There's utility embedded in such test screens, and especially traffic signs and other content-specific, automotive-specific objects are embedded in this test scene here. And of course, there's more array patterns. And this is only one static test scene. So it's important to realize that all of these metrics, these KPIs that we can measure on such a test scene are only for a static scene. And it's in perfect condition, so we haven't even explored parameter variations such as temperature of the camera. For dynamic scenes, you can imagine that there's other effects, and I'll get into this.